Okay, we're continuing on here with chapter 16. So last time we talked about obviously acids and bases. Um, Obviously, an acid is really something that can produce H plus ions or H3O plus ions in solution. Um, for acid-base chemistry, H plus and H3O plus, which is the hydronium ion, is essentially the same thing. They do represent really the acidic part of the solution. Bases, on the other hand, are guys that have the ability to produce hydroxide ions in solution. And what we're talking about here are free H plus, free H3O plus, and free hydroxide ions in solution. We talked about sort of definition of a Bronsted-Lowry acid and base, and a Bronsted-Lowry acid is a proton donor, while a base is a proton acceptor. Remember that sort of the consequence of this reaction is we do create sort of partners between acid and bases, and really what they form sort of on the other side of the reaction when they do react with each other. So really we have an acid and a base, and on the other side it will form a conjugate acid and a conjugate base. The acid on one side is related to the conjugate base on the other, and the base on one side is related to the conjugate acid on the other. Really, the only difference between these two things is that one H plus that gets transferred from the acid to the base. So the only difference that we can have is one H plus. So that is the only difference for a Bronsted-Lowry acid and base. As we talked about, even acids that have the ability to give away more than one hydrogen, it does happen sort of one at a time. So that's what creates our sort of conjugate acid base pairs. If it's anything more than one H plus, then it is not a pair in that situation. We then started talking about the idea of Kw, which is the equilibrium constant for water, or the ionization constant for water. And that is the concentration of H plus times concentration of OH minus equals 1 times 10 to the minus 14. That is essentially a constant, although as I mentioned, it does change with temperature, but pretty much for this class, that's usually the number you can use it in most classes. But if it happens to be not 25 degrees Celsius, then it actually does change. But we really usually do not have to worry too much about it. Remember that in this formula and in any sort of equation as well, these two guys are interchangeable. So once again, you may see it oftentimes written as H3O plus times the OH minus concentration. We could use this to really solve for the H plus concentration, which is the acid part, which is 1 times 10 to the minus 14 divided by the OH minus concentration. We could do the same thing to solve for the OH minus concentration. 1 times 10 to the minus 14 divided by the H plus concentration. It really is the same calculation, regardless of which one you're given. So if you're given sort of the acid part of the solution, you can figure out the basic part. And if you're given the basic part of the solution, you can figure out the acid part of the solution. And we can use this to help us determine if a solution is acidic, basic, or neutral. If the H plus concentration is larger than the OH minus concentration, so the acid part is bigger than the base part, then it will be acidic. If the base part or the OH minus part is larger than the H plus part or the acid part, it will be basic. And if they are equal to each other, then it would be neutral. And that would be a concentration of 1 times 10 to the minus 7 for each of them. We also got into the pH scale as well. And the pH scale runs from 0 to 7 to 14. And below 7 is acidic. Above 7 is basic. And as we talked about, we'll go with 7 on the nose there as neutral. 7 is sort of your center point. As you go towards 0, you become more acidic. And as you go towards 14, you become more. We can calculate the pH by taking minus the log of the H plus concentration. Once again, here you could also use the H3O plus concentration, which is the same thing. Remember that if you have a display calculator, you will punch that in exactly the way it's written. So you hit the negative button, the log button, then the concentration with your exponent. If you have a non-display calculator, then you got to go backwards. You got to start with the number, hit log, and then hit the negative button. Again, if you're not sure which one you have, all you have to do is hit log. And if it says log, you have a display calculator. And if it says error, you have a non-display calculator. We also talked about, I think there at the end, a scale similar to pH, which is the pOH scale. The pOH is equal to minus the log of the OH minus concentration. And really, both of those names really tell you what you need. To calculate pH, you need the H plus concentration. To calculate pOH, you need the OH minus concentration. We should always look at the pH value to help us determine if it's acidic, basic, or neutral, because that is usually the scale most people have in their head. The pOH actually runs opposite of the pH scale. So if you have a low pH, you have a high pOH, and vice versa. If you have a high pH, you have a low pOH. So they're opposites of each other. They're opposites of each other because the relationship between them is the pH plus the pOH will equal 14. So this does give you a little bit of variety as to how you could solve some of these problems. For example, if you have the H plus, you could just calculate the pH and you can subtract 14 and get the pOH, and vice versa. If you have the OH minus, you could get the pOH first and then subtract 14 and get to the pH. So it allows you maybe not to have to use KW, or you could still use KW and go traditionally solve it. They all should give you the same answer. I believe we also finished up talking about that if you have the pH, you could get the H plus concentration from that, and that is equal to the inverse log of the minus pH. And again, that on most people's calculators will pop up a 10 and a caret. Negative pH is really what you want. And you could also, if you have the pOH, get directly from it the OH minus, same calculation, the inverse log of the negative pOH. And that's usually a 10 and a caret negative pOH. Usually to do inverse log on your calculator, that is usually like the second button or shift button, top left corner, and your log button, which usually has like a 10 and X above it. And that is how you would do that, obviously. Same thing, if you have a non-display calculator, you actually do need to actually start with the number, make it negative, and then do the inverse log of it on your calculator. If you have a display calculator, just the way it's punched in there, inverse log, and then negative, again, not the subtract button, but the negative button, and pH or pOH. Any questions on any of that stuff we talked about, I think, the last time? All right, so I think we are here, I think. The pH of a solution is 5.67. What is the pOH? Why don't we do a few other things? Let's also do, what is the H plus concentration, OH minus? Okay, let's take a look. So we do have the pH. We'll start with the pOH, which is not too bad to find from it. Again, the pH plus the pOH does equal 14. That means that the pOH here would equal 14 minus our pH value of 5.67. So we'll take 14 minus 5.67. Going to give us an 8.33 as our pOH. At this point as well, since we do have the pH or POH, we can get the H plus and OH minus concentration. The H plus concentration would be the inverse log of the negative pH. So that would be the inverse log of minus 5.67. Once again, when you do this part on your calculator, most of them will put that 10. You want to make sure you make it negative there. In most cases, it'll look something like that on your calculator. And when you do that, negative 5.67, going to be a 2.1 to the minus 6. Since this is a concentration, we do need molarity given there. Also, another thing that we talked about was significant figures and sort of pH, POH calculations. In this case, we had 2 decimal places, which means when we go to the concentration, we should have 2 significant figures. So again, going backwards, that is what we should have. Remember, as you go from concentration to pH is significant figures to decimal places in this particular case. At this point, you do have a couple of options. We could use KW now that we do have the H plus concentration, or we can do the same calculation, which would be the inverse log of the minus POH. That's going to give us the inverse log of negative 8.33. Once again, on your calculator, it'll probably look something like this if you punch it in with your shift or second button in your log, and you will get about 4.7 times 10 to the minus 9. It looks like also again needs a molarity calculation there. Any questions on any of those values there? Again, if you use KW, your OH minus would be 1 times 10 to the minus 14 divided by 2.1 times 10 to the minus 6. And with a little bit of rounding, you get something like that, maybe 4.8 if you went that route. At this point, we want to know, is it acidic, basic, or neutral? And as we talked about, you want to make sure that you always look at the pH value. And in this case, the pH value here is a 5.67, which means a reminder that there is not more than one answer. That's either acidic, basic, or neutral, not all 3 of them together. Your calculator ran out of numbers. So if you put it into scientific notation, which I think you could do here, go that way. There. Yeah. So if you don't have a scientific notation, what happens is it puts in decimal. If you run out of numbers, it just rounds that last one. So that's why I got rounded to a 5.
So then with this calculator, make sure you put it into scientific notation.
Yeah, if you want to, yeah, you can leave it in that. Right now, it'll be left in that. I think so. All your answers will be scientific notation. So if you don't want that, I think you go back. That's where it was. I think I'll flow. So that, but if you see that, you could put
So
in
the
the
last one I got it.
Yeah. Yeah, so that sometimes happens is like your calculator doesn't have enough spaces to do like at the end 4, 6, whatever it is. So it rounds it. But if you do put in scientific notation, then you'll be able to see the rest of the numbers. Happened to you on the last problem. If your calculator was not in perhaps scientific notation, you might have got like a bunch of zeros and a 5 at the end on your calculator. And that does sometimes happen when you're doing calculations. If your calculator is sort of in decimal form and it runs out of space, what it's going to do is basically just lay up a bunch of zeros and sort of round the last number and stuff like that. So if you need to, you can put your calculator in scientific notation to get the answer. Or if you went with 5, you would have, with the right number of decimal places, 5.0, something like that, you would have been okay, in terms of the answer. But that's what happened and why I got like 4.6, whatever it was, or 4.7 on that last one. Sometimes if this is in decimal form, your calculator runs out of room basically. So it just rounds that last number. All right. So on this one here, we have the pH. So remember, from the pH, we can directly get our H plus concentration, as it basically tells us that there. And once again, this would be the inverse log of the negative pH. So again, punching that in, we will end up with, in this case here, not that, let's try that again. Let's see here. I'll try that again on my calculator now. That's don't want to cooperate. There we go. There you go. We end up with 7.2 times 10 to the 1, 2, 3, 4, -4 molar in this case. Any questions on that there? Obviously, yeah. Yeah, so in this case, so the rule is when you're calculating something like pH or POH is the number of sig figs in your concentration number is equal to the number of decimal places in like your pH or POH type value. So in this case, what we're doing is we're actually going backwards, which means the number of decimal places should equal the number of significant figures, not decimal places in the concentration. So in this case, we had 3.14, which has 2 decimal places, which means when we come back over here to our concentration, it should actually have 2 sig figs. So remember, we're kind of going from sig figs to decimal places back and forth, depending on which way you're going. So it's not decimal places to decimal places or sig figs to sig figs. Other questions? And again, when a number is written, obviously in scientific notations, we talked about all the numbers before the times 10 part are significant. So 7.2 would give us 2 significant figures. Other questions? All right, let's try another one here. POH is 5.67. What is the OH minus concentration? Are you asking on, I'm sorry, on this one or the last one? Can you use KW? You can if you have the H plus concentration. So in this particular one or the previous one, we really didn't have the H plus concentration, so there's no way to use that. Yeah, it depends on what they give you. So for example, the previous problem that we just did there, wherever it went, there it is. For example, if we were also asked, what is the OH minus concentration? Now that we have the H plus concentration, we could use that 1 times 10 to minus 14 to figure out the other one. But just from what they gave us in that problem and also this problem, we don't have that value, so we can't really use it. Okay, so let's take a look. So again, we do have the POH, which means we can get the OH minus concentration from it, which in this case would be the inverse log of the negative POH. And as was the question a second ago there, the reason, again, we cannot use this relationship at this point is because we really don't have any of those values. So we can't solve for it. So really, we're kind of stuck based on what was given to us to kind of go this approach here first. So if we did that, that would give us the inverse log of negative 5.67, which again is something like this. And if we do that, looks like we get 2.1 times 10 to the minus 6 molar would be our OH minus concentration. And as I was saying, at this point, if it also did ask you for, say, the H plus concentration, now you have the ability to kind of use the KW. And if you did want the H plus, you could go into here using the value you just calculated. And you could get the H plus concentration, which in this case would be something like would be something like this if I hit the buttons. There you go. 2.1 to the minus 6. Looks like 4.8 to the minus 9. This would also be another one that if you did it without scientific notation, you probably get a bunch of zeros and a 5 at the end of your calculator if you did it that way. Alternative to that as well is if you wanted the H plus concentration, you could get the pH first if you wanted to. And then once you have the pH, you could do the inverse log of the negative pH to get to your H plus. So there are a couple different sort of routes as to, depending on what's being asked, as to how you could get there. They all really should get you to the same spot. You know, might be slightly different depending on where you round it, but not an extreme difference. You know, maybe it's just with that like point number there at the end. Any questions on any of that there? Questions on how to calculate H plus, OH minus, pH, POH. You need to be able to do all those calculations. Yes. Okay. All right. So let's talk a little bit about pH of a strong acid. If we did have a strong acid, remember we sort of made a list of some strong acids. And just to remind you, some of those strong acids we talked about, HCl, HBr, HI, HClO4, a little nitric acid, a little sulfuric acid. So if we do have a pH of a strong acid, what's a pH? They may generic H plus or OH minus or H3O plus sort of concentration. It may actually give you, you know, an actual formula. And if it is a strong acid, as we talked about, basically it will 100% break apart in that solution into H plus, for example, and Cl minus in this example here. And as we talked about sort of molarity, if we know the molarity of the entire acid, we just need to really figure out the molarity of the H plus part. And we talked about this when we talked about concentration. You can kind of do it like a stoichiometry relationship. It's a 1-to-1, which means the molarity of the H plus would be the same as the HCl in this case. And that's really all you need for minus the log, say, of the H plus. Now, if you also had a strong base, for example, remember a lot of strong bases have hydroxide in them. It would work the same way, say something like sodium hydroxide, if it was a strong base, would also 100% break apart into a sodium ion and a hydroxide ion in solution. Now, unlike an acid though, because this is a base, we would actually be interested in the OH minus concentration. The OH minus concentration will not give us the pH, but it would allow us to calculate the POH, and then we could use obviously that the pH is 14 minus the POH. So you can even do this obviously with a strong base. You would want to figure out the hydroxide concentration. That would allow you to get to the POH, and then that would get you to the pH from that point. I would say for our purposes, again, if you sort of see a formula of an acid or a base and they're asked to calculate the pH, it is probably going to be a strong acid or base, because the calculation of a pH of a weak acid or weak base is much, much more complicated. So you will do that in 1B. So I would say it would be pretty safe if you're, again, given sort of an actual formula in this particular class. You could probably safely assume it's probably a strong acid or a strong base, and you could either figure out the H plus or OH minus concentration and then allow you to figure out the pH. So for example, if we did have a 0.1 molar solution of hydrochloric acid and we wanted to know, what the pH was, we would do our same sort of concept here. We would take our hydrochloric acid. We know it's monoprotic, so it will break apart into 1H plus and a Cl minus. We know that the concentration of this whole thing is 0.1 molar. So once again, it is a 1-to-1 relationship between those two things, as we talked about, which means we basically take 1 times 0.1 molar, and that would give us obviously 0.1 molar. So that 0.1 molar would be the actual concentration of the H plus that's in the solution. And once again, that would be all we would need to calculate the pH, which would be minus the log of 0.1 molar. And that's going to give us a pH of 1, I believe. There we go. pH of 1 here, which is definitely acidic, which is good because this is an acid. So I would hope it would be acidic in this case. Any questions on that there? All right, so why don't you try one here? Why don't you do this, and why don't you also let's calculate the pH of 0.025 molar. We'll do calcium hydroxide. You can assume it's a strong base in this example. All right, so calculate the pH of both of these guys here. See what you come up with here. Yeah. When you put the, like with the one we just did there, where you did the negative log. No, you just need to make sure you do use your, if you have a display calculator, you want to make sure that you hit the negative button, not the subtract button. So the negative button, then the log button, the LOG button, and then you could just put 0.1 hit equals. If you have a non-display calculator, you would do 0.1 first and then hit log and then make a negative button. So you kind of go backwards. Chloric acid, which is on that list of one of our strong acids. So once again, we do know that when this is in solution, it will break apart into H plus and perchlorate, basically. And in this case, we do know the concentration of the whole thing here, and it is a 1-to-1 relationship for the H plus, which is really what we need for the pH. So that means really it's 1 times 0.025 molar, gives us 0.025 molar for our H plus concentration. So we could go into our pH, which would be minus the log of 0.025. Once again, if you have a display calculator, you're punching that in exactly the way it is written. If you have a non-display calculator, you are starting backwards and going in that direction, depending on your calculator. So once again, display this way, non-display calculator going that way. So we do that whichever way you need to punch it into your calculator. Looks like we will get a 160 here, 1.60. Again here, two significant figures in our concentration gives us, once again, not two sig figs in our answer, but two decimal places for the pH here. And this does make sense because that is an acid and that is an acidic pH. So, you know, if you got like 12 here, that would probably be wrong somewhere along the way. Something probably didn't go so right. First off, any questions on that there? Looking at our second one, we're going to consider here a base because it does have hydroxide, and when it's in solution, it will break apart into calcium and a couple of hydroxides here. Concentration of this guy was also 0.025 molar. In this case, we actually are interested in the hydroxide, which is a 1-to-2 relationship. So that means we would need to actually multiply this by 2 to get the proper hydroxide concentration, which would give us obviously 0.05. That, once again, though, is the hydroxide concentration, which means we cannot calculate the pH from that. We can't calculate the pOH from that, which would give us minus the log of 0.05. And that gives us minus the log of the answer. That's about 130 there, 1.30. Now, if you did make a mistake at this point and you thought this was the pH, a pH of 1.3 would be acidic, and this is a base. So that, again, that should not make sense to you. So hopefully you'd be able to recognize that you didn't really calculate the pH, but you did calculate the pOH here. To get to our pH, we would need to take 14 minus the pOH, and that would get us 14 minus 1.30, and that would get us about 12.70 pH, which is a basic pH, and obviously that would make more sense in this case. Any questions on that? In our case, we did have to sort of adjust the pH, the hydroxide concentration, because it did break apart into 2. So you got to take that into account. But a lot of times it will be a 1-to-1 relationship between H plus and OH minus, but sometimes it may not be. So you do have to sort of take that into account. Any questions on either of those there? Okay, then the last thing we're going to talk about in this chapter are buffers and a buffered solution. Good talk. So first off, a buffer is a solution that's able to resist changes in pH when you add a strong acid or strong base to it. A misconception that sometimes people have about a buffer is that it is a neutral solution, and a buffer can be a neutral solution, but you could also have a buffer that's an acidic solution, a basic solution, a neutral solution. You could actually make a buffer at any pH you like, and it will basically be there. And really what a buffer is whatever pH that solution starts at, even if you add additional acid or base to it, it will be able to, if it's made properly, maintain its pH. Will it go up or down a little bit as you add acid or base to it? The answer is yes, it will. But what you will not see is really big jumps in pH. So for example, if I made a buffer at a pH of say 5 and I add some acid to it, I would expect the pH to remain around 5. Maybe it goes down to 4.9-ish or something like that. I would not expect the pH of this buffer to go from 5 all the way down to 1. It's not going to be acting as a buffer in that case. So not a really giant jump in pH. Same thing if I took that same buffer at a pH of 5 and added a base to it, I would expect the pH maybe to go up a little bit. Maybe it goes up to 5.1, 5.0 something, depending on how much I add. But I wouldn't expect the pH to go from 5 all the way up to like a pH of 12. They're really big jump in pH. So in reality, the buffer will move a little bit if it's made properly and what you're adding is okay to it in terms of the pH, but you will not see a giant jump in pH one way or the other if it is made really properly. The way we make a buffer is it has to be one of these two combinations. It has to be made up of either a weak acid and the salt of its conjugate base, or you can make a buffer out of a weak base and the salt of its conjugate acid. You cannot have a buffer that's made out of a strong acid or strong base. So there is no buffer that is basically made up of a strong acid or strong base. No. So the reason for that is actually the difference between a strong acid and strong base and a weak acid or weak base. The difference is when you have a strong acid or even a strong base, when it goes into solution, it will 100% break apart. And you have none of these guys still there. Which means when I take something like hydrochloric acid and I throw it into my beaker, I have H plus and Cl minus, which means in the actual beaker, really the only thing I have is a conjugate base. I just have a base basically in there at that point. I do have some H plus obviously floating around, but I have really just a conjugate base. I don't have the acid part, the HCl part still together. Same thing if I threw in something like sodium hydroxide into a beaker, you would have some sodium, you would have some hydroxide. You would basically have the conjugate acid there, the sodium ion floating around. You would not have the base part there. And what makes a buffer, as we'll talk about here, really function is the ability to have both an acid part in the solution and the base part. And the only thing that's able to do that is a weak acid or weak base because they are weak electrolytes. So if you took something like HF, which is a weak electrolyte, as we talked about, and a weak acid, when it goes into solution, you have H plus and you have F minus, which means when you throw a solution of that in there, along with a little bit more F minus, you will end up with HF still in the solution, and you'll end up with F minus. You'll have some H plus as well. But you will have basically an acid part in that solution and you will have a base part still in that solution. And that's really important for how a buffer is able to function and maintain the pH. And the only way you can achieve that is either with a weak acid or a weak base, because they will set up an equilibrium in that solution. And that will allow to keep both of those things actually in the solution at the same time. And that's what makes up a buffer, is actually having both of those things, the acid part of the buffer and the base part of the buffer, in solution at the same time, and pretty good concentrations, pretty good amounts basically in that case. And that just does not happen when you try to do it with a strong base or a strong acid. You only get basically one thing in the solution. Either the base part stays there or the acid part stays there. You don't have both of those things that are really there. Any questions on that so far? So let's talk about really, how a buffer works and how a non-buffer really works. So let's start with what happens when we do something that is not a buffer, like our good friend water. So water is not a buffer. And what happens to water when we basically add a strong acid? So if we add HCl to water, what is going to happen is we're basically going to have this guy break apart into H plus and Cl minus. So basically in that beaker, what we just did is we just added a bunch of H plus that's free floating and some Cl minus. And what we would expect to happen in this case is, we think about the pH equation, which is minus the log of the H plus concentration. By dumping this guy into water, we just generated a lot of H plus, which means the concentration of H plus goes up a lot, which means the pH will go down a lot. So we will get a really big jump in the pH when we add something like hydrochloric acid to water, because it generates a lot of free H plus, and that's makes the pH go down a lot. So in this case, it may go from a pH of 5 down to like a pH of 1, because you created a lot of H plus really, really quickly. And that obviously is not a buffer, so it wasn't able to maintain its pH. Remember, what really affects the pH of a solution is these two things. It is the free amount of H plus in the solution or OH minus. And that is because they are related to each other, as we talked about. As the H plus concentration goes up, OH minus concentration goes down, and obviously vice versa in this case as well. So those are really the two factors in solution that affect the pH of that particular solution. And again, is free H plus and OH minus, not attached to anything, just floating around freely in the solution. If we then took, say, a strong base and we added it to water, so we added some sodium hydroxide to water, once again, because sodium hydroxide is a strong base, it will break apart into sodium ion and hydroxide ion, which means, once again, we take a look at the solution. What's going to happen is we now have a bunch of sodium ions, and we have a bunch of hydroxide ions floating around in the solution. And we just created a ton of hydroxide ions, which means that the concentration of hydroxide will go up. That means the concentration of H plus will go down. And that means that the pH will jump up really high. So in this case, because we kind of just flooded the solution with a lot of free OH minus, just like we did up here with a lot of free H plus, the pH is going to jump a lot, because that's really the two things that can affect the pH, is those guys' concentrations. So that is why water here is not a buffer, and why we would expect to see a really big change in pH when you add an acid or base to it, because basically it's unchecked, the amount of H plus that you're doing. When you add the acid, you're basically just dumping H plus in there. And when you add the base, you're basically just dumping OH minus in there. Any questions on that there? So let's see what happens, though, if we add the same acid and base to a buffer situation. So let's say we had a buffer, some popular buffers like acetic acid is a popular buffer with sodium acetate. That is a weak acid. Whoops. And its conjugate base is known as the salt of its conjugate base because it has a sodium. We could use HF, which is a weak acid, and something like sodium fluoride or potassium fluoride. That is, again, a weak acid and its conjugate base. Or, you could even use a weak base like ammonia and ammonium chloride, which is a weak base and its conjugate acid. So we'll take one of these examples here. We'll do the popular one everybody chooses. Now we'll do this one. We'll do the one nobody chooses. Everybody chooses this one. We'll go with this one here, which is hydrofluoric acid. Yes, sir. Thank you. Good. Yep. Acetic acid is like the popular choice for buffers, but it is a very wrong. You're going to make one today, which is acetic acid and sodium acetate buffer. But we'll go with this one here. And so basically what we have in solution is when we start with this buffer of HF and sodium fluoride is this. We have in the solution, because HF is a weak acid, when it goes into solution, it's basically going to stay together. And it's going to create H plus and really F minus. And really, the F minus here is really this guy. That is basically the part of the buffer that really is actually doing there. The sodium ion is really there just to balance out the charge. It's really a spectator ion. It's really not doing much. It's really the F minus there that's actually doing the buffering part. And that's the conjugate base. So if you think about our Bronsted-Lowry definition, HF and F minus, that is a difference of 1 H plus. So that is definitely a buffer situation and a weak acid and conjugate base that is together. So by making this buffer, what we really have floating around in that solution is really HF and F minus. And that means that in solution, we're able to keep both of those guys in there. And we basically have a acid part to the buffer. And we have really the base part to the buffer. So both of those guys are in there. They're in there in pretty good concentration. If you make a pretty buffer, you got them in there at good concentrations. So what happens now when we take our hydrochloric acid and we add it to this buffer? Because this is hydrochloric acid, will it react with the acid part of the buffer or the base part of the buffer? The reactions are called acid-base reactions, right? So when you dump in HCl into here, what's going to happen is because this is an acid, it is going to react with the base part of the buffer in this case. And you will get a reaction here of sodium fluoride, which is basically the base part of the buffer. And this really is a double displacement reaction, right? Positive guy, positive guy, negative guy. And what we're going to get is HF going to be formed. And our sodium chloride here will be formed as well. So different than when we dump the HCl into water, we actually get a nice reaction that's going to happen here with the base part of the buffer that's in there. So really our acid and our base part of the buffer, and this is the acid part of the buffer is actually made. And that is what always happens in a buffer situation. We actually use up some of the base part of the buffer, but in the process of doing that, the reaction will actually generate some of the acid part of the buffer. So really HF was in there to begin with, so that's not going to screw up the pH. And the other thing that we're left with is a salt, which is this case is actually a neutral salt, and it will not mess up the pH either. But it is actually what we do not see in this reaction that we do when we react HCl with water. That is really the reason why it is able to work great as a buffer, and that is what is not here. Whoops. What is not here that was there in the previous page? If we go back, when we reacted HCl and water, we generated a bunch of H plus, right? Generated a bunch of free H plus when we dumped that into water. When we dump that exact same acid into this buffer, there is no free H plus formed, right? The H basically ended up with the base there, right? It got tied up, it's not freely floating anymore. And what that means is because we didn't produce any more free H plus, the concentration of H plus that it started with, which is right here, stays relatively constant. And because the H plus concentration really didn't increase or decrease by a lot, that means that the pH will remain relatively constant as well. So in this particular case, when we added the strong acid to our buffer system, because it had the base part there, it was able to react with it and basically tie up the H plus from becoming free in the solution. So it tied up the H plus, and because it didn't produce any more free H plus, which is really the thing that affects the pH, it basically meant that whatever H plus concentration we started with is pretty much the same. And that means that the pH will stay pretty much the same, and you would not see a really big jump in pH. In reality, like I said, you will generate a little bit more H plus because you made a little bit more HF. So you'll see the pH go a little bit, but you will not see a really giant jump in pH because it was able to maintain the amount of H pluses in that solution. Any questions on that there? Now, what happens when we add our base here to our buffer? So we'll do it here. So when I add my sodium hydroxide to my same buffer situation where I have my HF and F minus, when I add this sodium hydroxide, it is actually going to react with the base, the acid part of the buffer. So when I add my sodium hydroxide in, it is going to find the acid part of the buffer, and we're going to basically have a reaction between sodium hydroxide and hydrofluoric acid. And in this case, it is also basically an acid-base reaction. So we will make water, and we will make sodium fluoride. Once again here, we produce water, which obviously will not screw up the pH. We produce the other part of the buffer, which was sodium fluoride, which will not screw up the pH. But once again, it is actually what we do not see there that we did see when we added the base to the water. When we added the base to the water, we made a lot of OH minus. And in this case, we did not make free OH minus, which means the concentration of OH minus is relatively constant. And because OH minus and H plus are tied together, that means that the H plus concentration will also be relatively constant. And because both of those are pretty much not moving, the pH will stay relatively constant as well. So in the case of when you add a base to a buffer, because there is an acid part, it will prevent the formation of free OH minus in the solution. By doing that, what it essentially will do is keep the H plus concentration relatively constant, and the pH stays constant. First off, any questions on that there? So really the way a buffer is truly able to function and maintain pH is the crucial part of that is it has an acid part to the buffer and a base part to the buffer. And because both of those things are in the solution, when you add more acid or base to it, is able to prevent the formation of free H plus or free OH minus. And both of those things will keep the pH relatively constant. So for example, here, you think of it like this. So when you make a buffer, once again, you have, Let's do it a little bit smaller here. So when we make a buffer, we have basically an acid part and a base part, which in our previous example would be like HF and F minus, basically. That's the acid part and the base part of the buffer. When you add acid, additional acid to your buffer, what's going to happen is the acid and the base are going to react. And what happens is you will use up some of your base part, but you will make some of your acid part in that reaction. So you'll use up some of that base part of the buffer, but you will make some of the acid part, which is why a buffer is able to maintain the pH over a good period of time, because you're actually kind of generating some of it as you're adding some or base to it. When you add base to a buffer, it will react with the acid part, and dramatic drawing here, the base part of the buffer will increase, the acid part will decrease in this case. And again, the goal here is it prevents the formation of either free H plus or OH minus, and that is what really helps maintain its pH. Now, there is a limit to how well a buffer could work, and it's based on really the concentration of the buffer and also the concentration of the acid or base that you're adding. Let's just say that, you know, you didn't read the instructions, which would never happen, I'm sure. And you grabbed your acid and you're adding it to your buffer, but you grab maybe the wrong molarity, like, you know, 18 molar instead of like 0.1 molar. It could happen, I suppose. And you're adding a bunch of it, or you just keep adding the acid to the buffer. So if I keep adding the acid to the buffer in this case, what's going to happen to the buffer? The base part will continue to get used up, right? At some point, there is going to be no more base part, right? And if I continue to add more acid at that point, I'm going to start adding basically more H plus, and you basically blew through your buffer. And it's at that point that you would see a big jump in pH, because at that point, you're just adding more H plus. It has no base part to handle that H plus that's coming in. That's what sometimes referred to as buffer capacity. There's a capacity to how well and how long a buffer will work for. And either you add too much of an acid or too much of a base, you could actually blow through it. Or if you add the wrong concentration of acid or base to it, you can blow right through it. It may not be functional. So when you do make a buffer, you do want to think about two things. You want to think about the molarity of the buffer you're making, and you also want to think about the molarity of the acid or base you may be adding to it, and make sure that they are appropriate for each other. Any questions on that there? So once again, this table sort of summarizes it. Again, it is a weak acid or a weak base with its conjugate partner. It resisted changes in pH by preventing any free H plus or OH minus from basically accumulating in the solution. And again, it basically does either a sort of acid base reaction or a double displacement sort of reaction. And both of those basically up the H plus and OH. And that is the goal of allowing the pH to stay pretty constant, is keeping the H plus relatively constant. Any questions on how a buffer works? So again, common buffers, like I talked about, acetic acid, sodium acetate, like I think we'll do in lab today, HF, F minus, ammonia, and ammonium chloride. Carbonate type buffers like in your body as well, common ones as well. So it does again need to be a weak acid or a weak base for it to be a buffer. For our purposes, the way you can sort of identify that is the Bronsted-Lowry definition. First, you want to make sure that they are related to each other by just a difference of 1 H plus. If you're trying to decide, can these two things make a buffer? The second thing that you want to make sure is neither of those guys is a strong acid or